Hello, today we will be using physics to determine the fastest possible speed of this object on 3 separate ramps. We will do this by using 3 formulas. The first being the sine theta equals opposite side over hypotenuse, which utilizes the easily measured height and distance of a ramp to determine the angle of the ramp. Second, we will use the acceleration equals g sine theta formula to determine the acceleration with the angle and the constant 9.8 meters over seconds represented by the g. Finally, we will use the formula change in time equals square root of 2 times the change in x divided by acceleration t that can be used to find the time it takes the object to get down the ramp.
So first we're going to look at where these formulas come from. The first equation comes from trigonometry, where we know that sine theta equals the opposite side divided by the hypotenuse. Since we want to find theta, not sine, we'll want to divide sine to get it to the other side. And that is where the negative power sine comes from, because that is the same thing as 1 divided by sine, and that is where we then plug in the opposite and the hypotenuse of the ramp, and we are able to determine the angle, which we will need for this formula. In this formula, we use it to find the acceleration. Now, the deal with g is that g is the acceleration of free fall, or 9.8. Basically, if I were to just drop the car, this would be its acceleration, because it would just be in free fall. But we know that it's not in free fall, it's on a ramp. So we have to times it by sine theta in order to find out the acceleration due to the ramp, instead of that is preventing it from being the acceleration of free fall, which is why we use this formula. And the last formula is the most complicated, which is the formula to find the time it takes to descend the ramp. Now, this formula is actually a rearranged version of this formula right here, which is used to calculate the change in position. And what you'll notice about these formulas is that the first one is actually the area of a rectangle, with the initial velocity being the height and the time being the width. And similarly, this plus right here, this is the area of a triangle, with acceleration being the base and t squared being the height. Now, why is that important? Why would we be finding an area of a rectangle and a triangle? Well, what we're actually finding is the area under a velocity graph. And what you can find here is that the blue rectangle's area is velocity, the initial velocity, times time. And that will get us that guy, and then that is plus the red triangle's area, which is 1/2 acceleration times time squared. Since this original equation solves for the change in x, or the change in position, we know that the area under a velocity graph is the position. This checks out. And so we rearrange this, and also note that velocity is obviously going to be 0 because this car starts at rest. That tells us that this guy kind of just gets eliminated, which is why we result in this formula. And that is how we use each of these formulas. Thank you.
For our first experiment, we will be looking at a ramp that has the length of 44.5 in terms of just the overall ramp. It has a height of 15.5, these are centimeters by the way, and it has a length down here of this number. Now this number is very big, and that's intentional because we don't want to round it until we get to the end to get the most precise number possible. Now we start with our first equation, where we plug in the opposite and the hypotenuse right here, and from that we get this number here. This is the degrees of our angle. We can then take that number and plug it in here, and then we are able to get our acceleration. Specifically, we plug it in here, and we are able to get this as our acceleration. After that, we plug it in to our final equation here. Again, I'm not rewriting all these numbers because I am using their full unrounded, and I don't want to take up too much space or time, but this is the answer we wind up getting. And since we round at the end, we are also able to see what the rounded number is. So overall, with this ramp, these are the time it is expected for the car to take when rolling down the ramp.
Here we have the experiment for ramp 1, As you can see, the predicted time we calculated is very close to the actual time it takes for the car to make it down the ramp. And when taking into account significant figures, it's exactly the same.
This is our second ramp that we will be using, and its dimensions are listed below. And here we have our last ramp that we will be using. Again, its dimensions are listed below.
This table displays the final results for all 3 ramps used. The calculations made for each ramp are all very close to the actual time, and when accounting for significant figures, they all result in the exact time calculated. This data shows that these formulas can be utilized to accurately calculate the speed of a car going down a ramp.